Okay, so now we want to look at, since we have spoken about currents, how we can determine currents using this equation. So now we want to look at how can we measure currents within a conductor, within a circuit. Sorry. So we have an electric circuit. We have a potential, a PD that is applied within this circuit, and then we're going to have a load here, which is just going to be a bulb. And then we're saying this is a simple circuit, and within this circuit, because this is a circuit, a full circuit, right? So there is no switch, which means this is just this is a loop. We call this a loop. So now the current, because there's going to be a continuous flow of current within the circuit. So we want to measure the current within the circuit. What do we use? We use what we call an ammeter to measure current. We use an ammeter to measure current, and then in some cases whereby you need to measure small amounts of current, like tiny small amounts of current, we use what we call a galvanometer. But I think that you're going to do that when you're doing your labs. So now we measure we measure current using what's an ammeter, isn't it? So remember the SI unit of current is what? It's amps, isn't it? So we can represent the quantity of current in milliamps, micro, but normally it's just amps, depending on its amount. So now we are saying if the PD within this circuit is steady, if it's constant, if this PD is constant, if the PD within this circuit is constant, we are saying our current is going to be steady, right? Within the entire circuit, our current is going to be steady within the entire circuit. So the flow of the current is just going to be the same in each and every point within this circuit, isn't it? And then now we are saying how do we measure the potential difference within the circuit? This is our potential, right? A potential difference. You normally use a cell. At this level, you guys use a cell. Let me just draw another one. We are going to have your single cell like this, right? You have a single cell like this, and then you have your ammeter. An ammeter, this is the circuit symbol of an ammeter, right? This is the circuit symbol of a cell. So you need to know the circuit symbol. So how do you measure the potential difference of the cell? Potential difference, we represent it with using PTs. This is actually the same as voltage. The voltage across a component within the circuit. So what is the voltage, or what is the PT potential difference across the cell, across your cell, right? So what is the potential difference across this cell? So in order for you to measure this potential difference, we measure the potential difference using a voltmeter. And this is the circuit symbol for a voltmeter. We use a voltmeter to measure a potential difference within a circuit. And then we are saying the unit for PD are the volts. And then we represent them using the symbol V. The unit for PD, we are saying the volt. We measure using the volt, right? So now let's talk about something very important. You're saying within a circuit, within every electric circuit, there's supposed to be a supply, a source. There's supposed to be a source, and we're supposed to have a load, right? Supposed to be a source, the source of power within the circuit. Supposed to have a source of power within the circuit. Then we have what? A load, right? This is a load. This is where the power which is supplied within the circuit, this is where the power is used. Normally the load, it can be any component, but the most practical ones, the ones with resistance, can be a resistor, capacitor, or inductor. But those ones, we're going to look at them as you continue with your studies. So now our load here is our cell, right? This is the our supply is going to be this cell which contains a PT, right? So our supply is going to be this cell, and then this is going to be our load, and then of course there's a movement of current within this circuit. But this is what I want you guys to notice. If you're given a circuit symbol like this one, I'm just using one cell for now. This is the negative terminal of your cell, your battery. This is the negative terminal of your cell. This is the positive terminal of your cell. So remember, we said current moves from the positive to the negative, right? So this is the flow of current, because electrons are moving from the negative to the positive. So this is the flow of what? Of electrons. This is the flow of electrons. So you have to know the direction of the current if you're given a circuit like this, whereby you have your load here, and then now the smaller part of the cell is the negative terminal, the longer part is the positive terminal. So this is very important, which means currents flow in this direction, and then electrons are flowing in the opposite direction. That's the concept of conventional current. And then you are saying if the PD applied within this circuit is steady, we are saying which means that when the PD is constant, our current is going to be steady, right? So now we said we measure current using an ammeter, our PT using a voltmeter. So now I want us to look at something. I want us to look at resistance. Resistance impends the flow of current within a circuit, right? It's just a form of resistance. It resists the flow of current within a circuit. And we measure electric resistance. Using you're saying resistance, right? Electric resistance, right? So now we are saying an electric resistance, this is a ratio between the voltage and current. This is a ratio between the voltage and current, and we can determine the quantity of resistance within any circuit using what we call Ohm's law. So what is Ohm's law? Ohm's law states that the PT, or the potential difference across any conductor, is actually proportional to the current through that conductor, right? So I'm saying the PT through any conductor, not necessarily any, through what we call ohmic conductors. The PT through ohmic conductors is directly proportional to what? To the current through those ohmic conductors. So we'll see the nature of what we basically ohmic conductors. Those are just conductors that can carry electricity, isn't it? So, but not all of them, because we do have conductors that are poor conductors of electricity. Do you have conductors that are actually good conductors of electricity? So those ones that are good conductors of electricity, they fall under this category of ohmic conductors. So now we are saying within those conductors, the PT is directly proportional to what? To the current through those conductors. So now we know that V, remember PT we represent using the symbol V. So V is what? V is directly proportional to the current within those conductors, right? But since this is a proportionality equation, so now we need the proportionality constant. Then our proportionality constant here is going to be what? It's going to be IR. Then R is what? This R is our proportionality constant. R is the proportionality constant, and we are saying proportionality constant. So we are saying R is the resistance. So now our R is the resistance. Is the resistance. R is the resistance, right? So R is the resistance within the electric circuit. So we get the quantity of R using this. So which means our R is equals to what? V over I, right? Our R is the ratio between the PD across that component over the current, isn't it? So this is how it represents our resistance. And then you're saying our resistance is what is measured using the unit for resistance. The unit for resistance is what we use the ohms. We represent it using the Greek letter omega. So this is it. So now we know that in most circuits, in every circuit, in fact, in every circuit, there is resistance, right? There is resistance, which means in most electric components, there is resistance within that electric component. If we know the potential across that component, and also we know the current through that component, we can find the resistance of that component, which means we can find the resistance of a lamp, the resistance of a resistor, the resistance of an inductor, which we call it reactance. When you get to higher levels, you can see we can find the component, we can find the resistance of each component within an electric circuit. And then now, since we know since we have derived the equation for Ohm's law, we can actually graph this. We have a graph for which you call the IV graph. There's a graph what you call the IV graph. The IV graph, it actually reveals the characteristics of the ohmic conductors that I was talking about earlier. So for every conductor that obeys the Ohm's law, will when you draw the relationship between the current and the voltage within that conductor, they give you a linear graph, whereby we say if we have a graph like this. This is our current, right? This is our voltage. They all ohmic conductors, they all have a graph, which is a linear graph, right? And it passes through the origin between these axes. Our y-axis here is the current, our x-axis here is what is the voltage. So the slope, we represent the slope of this graph as 1 over r. The slope of this graph is 1 over r. So how do we get to this graph? So remember, we come back to our Ohm's law. V is equals to what? V is equals to I r, isn't it? So since our I is in the y-axis, since our I, this is a straight line, remember. So we are going to take this equation and form a straight line using this equation. So our y-axis is what is I, which means from this equation you have to make I the subject of the formula, which means I is equals to what? I is equals to V over R, right? And then we can just separate this, which means 1 over R times V, isn't it? So now, if we have this equation, I is equals to 1 over R V. Based on this graph, we can see that current is varying with what? With voltage. Current is varying with voltage, which means this is our gradient. So this is the same thing as y is equals to mx. So our v is our x because it's in the x-axis, and then our I is what? Is our y because it's in the y-axis, and then 1 over r is what is there. 1 over m is what is there, is our gradient, which means m is equals to 1 over r. So we are saying ohmic conductors they behave in this way. Ohmic conductors, they behave in this way. So there's a linear relationship between current and voltage, because we said V is directly proportional to I for every ohmic conductors. So conductors that don't follow this relationship, we call them non-ohmic conductors. We call them non-ohmic conductors, and they have a different graph. So we call them we call them non-ohmic conductors, or materials, ohmic conductors, and they're different. There are lots of them. But there are lots of them. We have filament. We have the filament lamps. We have diodes, transistors, and all of that. And their relationship is not linearly. This is the IV graph. That relationship is not linear. You see, we have a curve in this case, which means we don't have a straight line from the origin. So this is normally the graph for non-ohmic conductors, but the graphs for non-ohmic conductors, they differ depending on that conductor. So we have to do and then now let's look at the resistance of a conductor, of a conducting wire, if I may. Yeah, the resistance of a conducting wire. The resistance of a conducting wire. The resistance of a conducting wire. So we are saying, if you have a conducting wire, this is your conducting wire, right? This is your conducting wire. We have the length of the wire. L, right? Of course, there's a cross-sectional area. This is the cross-sectional area A of the conductor, isn't it? So now there's a relationship between these. So we are saying the resistance of the wire R, we are saying the resistance of the wire is directly proportional to the length of the wire, which means as the length of the wire increases, the longer the wire, the more the resistance within the wire, right? So as the length of the wire increases, the resistance also increases for the wire, right? And then also we are saying the resistance of the wire is inversely proportional to the cross-sectional area, whereby now we are saying if we increase the cross-sectional area of the wire, the resistance is going to decrease if we increase the cross-sectional area. So now we can see that our resistance is proportional to what? The resistance of a wire conducting wire is proportional to what? It's proportional to the length over the area, right? So this is a proportionality. This relationship is proportionality, right? So we need to find the constant of proportionality. Our constant of proportionality here is going to be rho, which we call resistivity. It's a quantity that we call resistivity. Resistivity, we represent it using the Greek letter rho. So now our resistance for a conducting wire is going to be rho times the length over what? Over the area. So this is the resistance of a conducting wire, or the resistance of an ohmic conductor. So and then this is the very important quantity. This is the most important quantity, which we call the resistivity, right? We call it resistivity. Is the most important quantity, and the unit for resistivity are what? Ohms meter. Is the ohm meter. Call it the ohm meter. We represent their symbol is the Greek letter omega multiplied by m. So you just have to make this, the substitute of the formula, the resistivity, and then you know the SI unit for you know the units for resistance, and then you know the unit for area and the length, and then you just derived you can derive the unit for resistivity. So this is a very important quantity when we are looking at electricity. So okay, so this is, and then now we've spoken about resistance, and now let's talk about conductivity, right? Let's talk about conductivity. Since there's conductivity within an electric circuit, and then there's also what resistance within an electric circuit. So now let's talk about conductivity. We are saying with conductivity, there are things that we have to bear in mind. Remember, we had our equation I is equals to NQVD times A, right? We had this equation, isn't it? So now there's a quantity that we have to know in order for us to understand the concept of conductivity. There's a quantity that we have to know, which is called the current density. It's called the current density. A quantity that is called the current density. And current density, it depends on the textbook that you're using, but we represent it using J. And then current density is we are saying current density is going to be what? Current density, which means current over what? Over the area, a cross-sectional area, isn't it? It's going to be current over a cross-sectional area. So now we know current, right? We know this is the formula for current, isn't it? So we can just substitute our current here to get NQVD times A over A, isn't it? Times A over A. So with this one, our A is going to divide, right? So now we have our current density is equals to what? Is equals to NQVD, right? Is equals to NQVD. So this is very important. And the SI unit for our current density is equals to what? Is equals to amp over amp per unit square meter. Amp per unit square meter. So now if you are looking for the current density, this is the current density, but for electrons, when you're considering electrons, remember we said our VD, our drift velocity, was negative E over m, which is the mass of an electron times time, isn't it? So now our current density is going to be what? Our current density is going to be where there is VD, we substitute with this equation, right? So it's just going to have NQ, right? So we're going to have NQ, but sorry, since we're looking at electrons now, so our charge here is going to be what? Since we're looking at electrons, our charge is going to be E, because we're looking at elementary, because we're looking at electrons. So our elementary charge is going to be E. So J is equals to NE. Instead of Q, we have E multiplied by what? By the drift velocity, which is what? This is our drift velocity, which is E over ME times T, right? So this is what we have, right? So E times E is going to be what? E squared, right? E times E is going to be E squared. So we have NE squared, right? Times E, isn't it? All over M, which is the mass of the electrons, times what? Times the time. So this equation is very important, This equation is very important. So now when you're looking at this equation, let me just rewrite it. Remember, still looking at the concept of conductivity. So this equation is very important. So now we have our current density, which is equals to Ne squared times E over M times time, right? So now this is a very important relationship that we can get from this equation. We are saying our current density is directly proportional to what? To the electric field. It's directly proportional to the electric field. This implies that this is a proportionality equation, right? Which means there should be what? There should be a constant, right? A proportionality constant. So we are saying from this relationship we can say that J is equals to what? J is equals to, okay, depending, okay, I'm not sure about the symbols even here, but we use sigma times what? Times E. So now this is sigma is what? Is our proportionality constant, and these constants, since sigma is a constant, our proportionality constant, so our sigma is what? Our sigma is represent the electric conductivity. Represent the electric conductivity. So now, based on these two equations, you can tell that your sigma is what? Since we are saying J is directly proportional to E, right? Which means everything else within this equation is what? Is sigma, which means our sigma is going to be E. Our sigma is going to be Ne squared times time over the mass of the electrons. So this is our sigma. So we can find the quantity of conductivity using what? Using this equation. We represent the electric conductivity using sigma, but okay, it varies depending on the textbook that you're using. But this is the common one. So also we are saying the SI unit for electric conductivity is what? The SI unit for electric conductivity is going to be amps per voltmeter. So the units are very important, but you can derive the unit using the equation itself. If you know N, right? If you know the unit for N, the unit for E, the unit for time, and the unit for mass, you can derive the unit for sigma, which is our electric conductivity. We did derive the unit when we were looking at kinematics and the physics last semester. We did all of these things. So now let's go back to resistance. So there are factors that affect resistance. There are factors, and the major factor that affects resistance is what? It's temperature. Temperature affects resistance. This is one of the main factors that affect resistance. It's temperature. So in most cases, you find that when temperature increases, we are saying when temperature increases, resistance also increases. How is this possible? We are saying when temperature increases, since temperature increases, which means the atoms within the conductor will gain energy. And once they gain energy, they will start to vibrate, right? They'll vibrate. Once they start to vibrate, they'll vibrate with a higher frequency. So as they vibrate, the atoms within the conductor, as they are vibrating, we said current is the flow of charges, right? Which means the flow of electrons. So when these atoms within the conductor are vibrating, and these electrons are trying to move within these vibrating atoms, so the more they vibrate, the harder it's going to be for the electrons to move within the conductor, right? So that's why, and then which means the flow of the electrons is being impeded, right? Is the flow of electrons is being resisted, right? So that's why we are going to, that's why we are saying as temperature increases, resistance is also going to increase. And then we know that since resistance is directly proportional to resistivity, remember from this equation, right? Oh, this is A, sorry. From this equation, our resistance is directly proportional to resistivity, which means also when temperature increases, our resistivity increases, right? So this is very important. This is a very important factor that you guys have to understand. And we are saying our resistivity or the resistivity or resistance, they're directly proportional, isn't it? Which means as temperature increases, they are also increasing linearly with the temperature. So there are equations that you have to understand, the equations that you have to know that represents the relationship between temperature and resistivity. Let's start within temperature and resistivity and temperature and resistance. So let's start with temperature and resistivity. Temperature and resistivity. It's actually the same equation because resistance is directly proportional to resistivity. So we are saying temperature and resistivity. This is the rule. We are saying rho is equal, resistivity is equals to rho naught multiplied by 1 plus alpha t minus t naught, right? So what is going on with this equation? So we have rho naught 1 plus alpha t minus t naught, right? So we are saying this rho, this resistivity, we can call it the final resistivity. This final resistivity correspond to the final temperature, this temperature. So this final resistivity correspond to the final temperature, right? This initial resistivity correspond to the initial temperature. So this is very important. This is very important. And we are saying normally this initial temperature is taken to be greater or less than 20 degrees Celsius. It's taken to be greater or less than 20 degrees Celsius. And then also we have alpha. Our alpha, we call alpha the temperature coefficients of resistivity. So alpha is the temperature. Alpha is the temperature coefficients of resistivity. So it's very important. This is very important. So this equation is very important and you have to remember it. So even it's the same thing, this is temperature and what's this? Temperature and resistivity. And then even with temperature and resistance, still the same thing. R is equals to R naught 1 plus alpha t minus t naught, right? Still the same thing, whereby R is our resistance, it corresponds with the final temperature, and then our R naught is correspond with this temperature T naught, right? Okay, let me just erase this. Our R naught correspond with T naught, isn't it? So this is very important. So this is it about the resistance. And then okay, let's look. Remember earlier on I spoke about superconductors. Superconductors. So basically superconductors, these are conductors. These are conductors that have. These are conductors um, that have zero. These are the conductors whose resistance can decrease to zero, right? These are the conductors whose resistance can decrease to zero, right? So which means when there's zero resistance within that conductor or material, and this happens at certain temperatures. In order for this condition to be satisfied, it happens at certain temperatures, and that certain temperature below a certain temperature, which we call it the critical temperature. We call it the critical temperature. So this takes place below a temperature which we call the critical temperature. So above the critical temperature, that material or that conductor is not a superconductor, but below the critical temperature, it becomes a superconductor. So what does this mean? So now there's nothing really, when when current flows within this superconductor, there's nothing resisting the current, isn't it? Which means the currents can actually flow even without having what? Without having a PD across that conductor. So that's why superconductors are very important. They are very important. So these are just material and they're super rare, but their concept is very important. And so now let's look at the last part of this chapter where we are looking at electric energy. So within each and every circuit, there's going to be what? There's going to be energy. So energy is very important. So now we are going to look energy in different aspects. So what I want you guys to understand is that there's energy that is formulated by what? By charges, right? There's energy that is formulated by charges, because remember, as charges are moving, there's work that is done, right? So remember, we said when we're looking at when you're looking at the electrostatic potential of charges, right? And remember, we have within an electric circuit, we are saying there's flow of current, right? Which means charges are flowing, isn't it? And then, of course, we are going to have an electric potential energy of those charges. Remember, when we spoke about static electricity, we spoke about that concept. We said the electric potential energy of charges is equals to what? Is equals to the change of the charges times the PD applied times the potential difference, isn't it? So the potential difference we represent using V, isn't it? So this equation is very important. Our change in U is what's the electrostatic potential energy, right? It's still energy. This is our energy, but it's the electric potential. It's due to the potential, right? It's due to the what? It's due to the potential within this circuit. It's due to the potential within this circuit. So the PT across this set is the same as the PT across what? Across the entire circuit. So now this PT will formulate what? Will formulate an electric potential energy. So this is very important. So allow me, okay, I'm not sure about what symbols do you guys use, but allow me to use E for energy, and W for work done. Allow me to use E for energy, W for work done. So I can rewrite these because remember, E is the same thing as what? As work done, right? E is the same thing as work done. So I can rewrite this equation, because we are saying there's work done as the charges are moving. So work done is equals to what? Is equals to Q times V, which means in order for us to find the work done due to the charges, we multiply the quantity of the charge times the potential difference across those charges, right? So this equation is very important. We're going to use this equation to derive other to derive the equation for energy. So looking at this one, this is the work done, or the energy, due to the charges that are moving across a PD, right? So now we are saying our energy is equals to QV, right? Still the same thing. So remember, but we know that Q is equals to what? Is equals to IT, isn't it? E is equals to QV, but we know that Q is equals to IT. So now we formulate a very important equation whereby now we're saying energy is equals to what? Energy is equals, where there's Q here, we substitute by IT. So we know that energy is equals to what? Is equals to ITV. Normally we write it as E is equals to IVT. So this is very important. This is very important. This is the equation for energy within an electric circuit. This is how you find it. And if you know the current within the circuit, you know the time within the circuit, you know the time, you know the current, you know the PT across the circuit, and you know the time at which the electric charges or the electrons are traveling at, you can find the energy of that electric circuit. This is very important. This equation is very important. And then we are going to derive. So we are looking at electric energy, right? This is electric energy. We use this equation to calculate, to find energy. This equation is still the same thing. This is still the same thing, right? So now let's look at power. Let's look at power in a circuit. Power within a circuit. Power in a circuit. Let's look at power in a circuit. So let's look at power in a circuit. We are saying, remember, we are saying power is the rate of change of energy, right? Power